Um, so let's get going. My name is Sri Krishnamurthy, and I'm going to be the host of the show. I'm just going to do the introduction and hand over the reins to our amazing speaker today, Louis Serrano. Louis and I, we got to know each other at one of the conference circuits I get to. I forget it was ODAC or probably one of the other events in the West Coast. So we were doing some work with Udacity, and Louis was leading many efforts at Udacity on some of the machine learning and deep learning, and also the autonomous driving course, right? So that was your key course, and I was seeing a lot of cool experiments and things which Louis was working on. And fascinatingly, we kind of learned deep learning more or less in the same time frame. And it's kind of amazing to see how the world has progressed. And now Louis has taken one step further, and he's going beyond the binary, if you will, and he has moved on to quantum computing. And he's now working on some really amazing projects in quantum computing. And we thought we'll invite Louis to our Quant University Winter School 2021. As you all know, Quant University has been hosting the summer school and the fall school last year. And we have had more than 30 speakers who have given their time and shared their knowledge with the amazing quant and data science community in the world. And we have had participation from practitioners, from academics, from entrepreneurs, from investors, covering the gamut of various innovative frontiers on machine learning and AI, and how that's impacting practitioners, and how practitioners should be keeping their vision open to all the new possibilities that are out there. So we intend to continue this effort in 2021. As you all know, we are launching the Winter School 2021, and we have 3 courses primarily to facilitate the Quant University Machine Learning Certificate Program. 1 course to get you grounded with some of the data science concepts in Python. And then the second course is on machine learning and AI for financial professionals. And the third one is primarily risk management in AI, which is becoming a very hot and important topic as AI permeates throughout our lives and as we build out more and more capabilities. So I also want to call out Louis is working on an amazing book on machine learning, and he has promised to share a code which all the registered participants will get in an email later, so that you will be able to get a significant discount on the grokking machine learning book. And he'll also be sharing some of the links, I guess, on some of the things he's been working on. And also, I want to tell you a little bit about what we do for people who are new, and I'm just going to share maybe a few slides and then hand over the reins to Louis. So welcome again. This is 2021, and we are so glad to see you all, seeing the amazing participation from throughout the world. At Quant University, we have made a mission to make sure that we bring in a core foundation to the various aspects of machine learning and data science. And we have been building the capabilities, and we have been also building the Q sandbox, which is enabling operationalizing many of these themes. And as you all know, we have been building out various certificate programs and learning programs. And for people who are interested, just go to quantuniversity.com. That is QANTuniversity.com, and you'll be able to see all the amazing courses we are offering. And in addition to the various courses, we have also been launching the Winter School, which is going to include more than 12 weekly lectures. So it's going to be either on a Tuesday or a Wednesday, 60 to 90-minute sessions, so that you can continue your learning on various themes. And we're kicking off the session with Louis's workshop today. And it's going to be on generative modeling using quantum machine learning. And when Louis gets the stage, he'll be sharing the setup and the code, and also doing a deep dive on the various themes. So next week, we have another session. So it's going to be on machine learning in finance specifically, and things you need to know in 2021. And I'm also going to give you a flavor for some of the courses I'm going to be personally teaching over the next 3 to 4 months. For people who don't know me, I founded Quant University in 2013, and we made a mission to democratize education in machine learning and finance. I also hold an academic position at Northeastern University, wherein I teach courses on operationalizing in machine learning. And also I'm teaching a course on algorithmic marketing this time around. So I'm very excited to start the year looking at all the amazing things that are happening in the machine learning and AI space, and to see how that's going to impact us as professionals. So all the code and some of the links we're going to be sharing will all be available on q.academy. If you have not registered, please register at qu.academy so that you get access to the prior lectures and also the lectures we're going to be holding today, and then use the code QWinterScope. So that's my brief introduction, and welcome again, Louis, and I will hand over the stage to you.
Thank you very much, Sri. Very, very nice to talk to here, and thank you for the invitation. We certainly go way back and have similar goals with democratizing education. So when you told me about Quantum University, I was like, oh, I'd love to be a speaker there. So cool. Yeah,
I'm going to make you the host, so you will be able to share the screen. Yeah.
I'm going to try to figure out how to share my screen and also see the chat. Let's for the best.
Okay, so we can see your screen now.
Okay, I see a Q&A. Do you see the screen where you and I appear?
I see the slides.
Yeah, the slide. Yeah.
Yeah.
That should be it. Now let me present. And okay, so I have the chat right here, and I love to make everything into a discussion among all of us. So please make great use of that chat window. Ask me any questions. I will stop every now and then for questions. Any suggestions you have, basically anything you like. We have material for a long time, so I'll be picking a few things there, and so it depends on what interests I see that people are having. But the main idea is that I'm going to show you sort of a toy problem in quantum generative machine learning. So there's three words there: the quantum, the generative, and the machine learning. You don't need to know any of them. If you know any of them, it's fantastic. But I'll be introducing everything we need. But as I said, stop me at any moment as I go. Right. Now all I need is to pass the slides. There you go. So what we learned today, we're going to learn a little bit about quantum computing, a bit about generative machine learning, a bit about quantum generative machine learning, and then we won't do this, but I have sent links, and I'll give you more. There is a coding lab in PyQuil that you can do with some exercises, and there's also a demo of Orchestra, which is the platform at Zapata, which is the company where I work from, and I will tell you more about it. So what we do at Zapata is we work with in mostly business and research to enhance their quantum capabilities. So we sometimes companies need to have an engine for quantum computing, for quantum machine learning. They need to build their applications and need to be forward compatible. So they need to be ready for the future, when the present and the future, for when bigger quantum computing is arrived. They want to have their software and their algorithms there ready. And research, they need to accelerate their experiments, be able to duplicate them, be able to manage them. If you have code in TensorFlow Quantum, but also in PyQuil, and someone else has code in Qiskit, how do you put them together? How do you make a whole workflow out of that? And so that's the product that we have. It's called Orchestra, and I'll be telling you more links later. But basically, there are three main components. The first one is compose. You compose a workflow. You write the code. It's language agnostic, so you can write in many different packages: Python, Julia, QStar, and any package of machine learning or quantum computing. Then you can run this in several different platforms. So you can run it in different engines: IBM, Rigetti, IonQ, Honeywell. You can also use many different simulators, etc. And then this ties into places where you can handle the results. So you can handle the data with you can use pandas, JSON, the CSV, etc., Tableau. So it's kind of the whole package. I'll be showing you a demo later. Can I increase the size of some questions? Hi to the ones who are saying hi. Is there a live translation? I believe not. Please, can you increase the size of the slides? Is there a way, Sri, I think, for people to go and zoom and see the entire slide and a little me as opposed to half?
If people are watching over Zoom, then they have the ability to use two screens if they want to, and they can make it. But at least I can see it clearly, so it could just be very specific. Yeah.
Okay, perfect. Yeah, I think there's a button for making bigger. Just a little bit about myself. I started doing math in my life, and then I switched to machine learning. Worked at a few places in Silicon Valley after my life in research in academia, and then I decided to switch to quantum computing. As we mentioned, I have a book called Grokking Machine Learning that I'll be sharing a code later with you for a discount code. And I also have a YouTube channel. If you haven't seen it, it's you can search Luis Serrano on YouTube, and I have a bunch of videos on machine learning and sort of easy to understand. I try to make things, as you'll see my style, I try to make it very non-formulaic and just kind of more like visual examples. So I hope you enjoy that. And this hasn't been just by myself. It's I have two collaborators who help me with this talk, and we give it sometimes. One is Caitlin, who is an intern at Zapata, now a PhD student at Oxford, and the other one is my manager, Alejandro Perdomo, who's a quantum AI lead research scientist. Perfect. So yeah, basically just an overview of quantum computing in the same way that all roads lead to Rome, and all Wikipedia pages, if you click enough times on a link, leads you to philosophy. We're noticing right now that all industries are leading to quantum. Everything, finance, optimization, pharmaceuticals, chemistry, anything, they're starting to realize that quantum is the way to go for many reasons. It speeds up and improves the algorithms, and it certainly is the future of that. And the way quantum computing works, quantum machine learning, is very similar to the actual machine learning. You all you have to do is turn your data and put it into qubits, and then you can use a toolkit of many things, including optimizers and you manipulate this data, as I will show you, and get an output just like you do in normal land. And so you send this output to the cloud, which is the quantum computer. And the quantum computers, there's several different hardwares. There's ion trap photonics, superconducting, and as I said, many simulators that are very useful. So things that quantum computing offers is starting to notice greater model accuracy, also small time complexity, and it's not just a faster computer, it's the actual algorithmic time, like a smaller time complexity, and larger capacity for storage. And you'll see why, because qubits can store a lot more than a normal bit. So as I said, this is the format. First, I'm going to teach you some machine learning and then some quantum computing, and then we'll tie them together in quantum generative machine learning. I'm going to go over this. We'll have an intermediate intermezzo in the middle. And as I said, the coding, I will leave it to you to do on your own time. So first, what is generative machine learning? So more like, what is machine learning, right? So in machine learning, we have several branches: supervised, unsupervised, and others. Supervised machine learning is the most common used, which is you have a model, and the model, you give it some data. So let's say this robot is my model, and I give it data in the form of images of dogs and cats. And I now give it a new image that it has never seen. And I say, what is that? And we train the model to say that is a dog. So that is the most common machine learning techniques. And it's basically, you teach the computer how to answer yes or no questions, or how to answer questions in general, mimicking the data that you previously have. Now, there's also unsupervised machine learning. So in supervised machine learning, the data has labels like dog and cat. In unsupervised, it doesn't. So the computer cannot say this is a dog, this is a cat, but the computer can somehow find patterns and say things like, for example, well, I don't know what these things are, but these over here are different than these over here and are different than this over here. So it sort of, it tries to understand the data by just looking at it as opposed to just answering questions. So it's more of like a philosopher, just looks at things and goes, what is happening, right? And then a branch of unsupervised machine learning, which is very popular right now, is generative machine learning. If you have seen those algorithms that draw a human face exactly, and it's even hard to recognize that it's generated by a computer, those are generative models, and they're doing very well right now. So that's the opposite to supervised learning, right? In supervised learning, I give you an image and I ask you, the computer, what is it? In generative machine learning, I tell the computer what is it, and then the computer is supposed to draw an image of it, right? So it's backwards. And that's what we're going to do today. Why are we going to pick the hardest to turn into quantum as opposed to starting from the easiest one? For many reasons. One is that you'll see that, well, one is that supervised learning is very well done in classical computers. So it's not something you could enhance it, but it's already working so well and so fast and so optimized that it's kind of, you may make some marginal things, whereas generative learning is something that can really make an impact. And the other one is that you'll see that quantum computing leads itself to generation even much easier than classical computers. And it's called measurement, and we'll see it in a bit. So what's the difference between classical and quantum machine learning? Well, in classical machine learning, this is very high level. You have you have a network, for example, a neural network, and you introduce numbers, and the numbers get added, multiplied. You apply activation functions, etc., to, let's say, draw an image, and then you compare it to your data set in some way, and it tells you how far are you from drawing an actual image, and from that you update your parameters. Well, quantum machine learning is the exact same thing, except instead of numbers, you have qubits. And I'll tell you what a qubit is in a minute. But if you turn your data into qubits and you throw the qubits into your network, just like you did with numbers, and these get not multiplied and added, but they get transformed in certain ways, and then you read it back to numbers, you can get an image, and you again compare it to your data set and use that comparison to update parameters. I'm being vague, but I'll be more specific. With the numbers, you do things like you add them, you multiply them, you apply activation functions, etc. Well, with the qubits, there are several things you can do. You can rotate them, you can entangle them, you can apply quantum gates. There's many things you can do, but it's in principle, it's the exact same thing. So when you think of quantum machine learning, think of machine learning, but not done with numbers, done with qubits. Okay. And so there are some very popular classical generative models like GANs, RBMs, variational autoencoders. And for quantum generative models, we have pretty much, you can attach a Q to everything. There's quantum GANs, there's quantum Boltzmann machines, quantum circuit board machines, etc., etc. So today I'm going to tell you about one, a quantum circuit board machine. That's what we're going to learn today. One quantum machine learning algorithm, and you'll see that it's general enough that it gives you an idea of all of them. As I said, any questions, feel free to put them in the chat. So let's get to the meat of things. What is a qubit? So what is a classical bit, right? A classical bit, I see it as a switch, like an on-off switch, right? And this on-off switch can be a 1 or a 0. So for the duration of this talk, 0 is up and it's red, and 1 is down and it's blue, okay? In quantum land, you have a lot more than a switch. So, if you have in your house a dimmer that you can set into like high or low or like romantic or anything like that, that's more like a quantum switch, like a quantum bit. You can have the 0 state, which is up. You can have the 1 state, which is down, but you can have a superposition of states. You can have something right in between. You can have something that is 0 and 1 at the same time. It's kind of weird. That's the weird part of quantum computing, or one of the weird parts of quantum. But you can have it as both, and you won't know until you look at it. But you can also have 3/4 up, 1/4 down, or 1/4 up, 3/4 down, or any percentage you want, any ratio that you want, 97% up, 3% down, you have them all. And I'm going to express them like this. They're not expressed like this in the literature, but I kind of like this notation. I tell you how much of it is up and how much of it is down, and they're supposed to add to 1. So 25, 75, etc. Now, there is a lot more to that. Let me, 1 second. So the one that is half-half actually is, there's like 2 ways to do that. You can do half-half pointing to the right and half-half pointing to the left, and those are fundamentally different qubits. And somebody asked if Anish, is it continuous or discrete? The answer is it's continuous. So I can put any number you imagine between 0 and 1. But somebody noticed that you can have a half-half in 2 different ways. You can go left or you can go right. And all the proportions, you can have them in 2 ways. So you can imagine them pointing in these directions, right? So, and these can be written not as like 0.75, 0.25, but as like 0.75 minus 0.25 for some reason. And so what we really have is more of a circle. So it's not a dimmer that goes up and down. It's like a circular switch where you can be in any of these positions. However, there's more. There's not just 2. Somebody found out that there's many ways to have a switch on half up, half down. For example, you can have it pointing towards your face, right? That's another qubit that is different to the previous ones, and it's also half-half. As a matter of fact, imagine a sphere. Anything on the equator, any way you can point your finger in the equator, is a completely different qubit that is in half-half superposition. Okay. I see a raised hand. You can feel free to just throw your question in the chat, actually. And actually, in any point of the sphere is a full superposition. Is some qubit in some superposition. So we have the North Pole, which is full up, the South Pole, which is full down, any point in the equator, which is a different half-half, and any point in basically anywhere in the sphere is that proportion. The proportion is how high you are, how close to 1 versus how close to 0 you are. And those are the qubits, and that's called the Bloch sphere. Now, for some technical mathematical reason, it's not 0.5, 0.5, and 0.75, 0.25, but it's actually like square roots. You need square roots for this to make sense mathematically. So everything is square root of something up and square root of something down. And I drew them in green so that if you want to forget about square roots and just find the proportions, put on your green glasses and you won't see the green. So I have a quiz for you. And the quiz is, if the point to the right is square root of 5, square root of 5, and on the left is square root of 5 minus square root of 5, what do you think is this one? Tell me in the chat. And meanwhile, I'm going to see if there are questions. If you see that I miss a question, feel free to... Oh,
yeah,
there's also a question and answer.
Louis, I'm going to read it for you. So how are weights in quantum machine learning saved and reused later is the first question.
Yeah, I actually see them.
Okay, perfect.
Yeah.
The second one is...
so I'm going to answer AJ's question. How weights in quantum machine learning are saved and reused later? I'll get to there. It's hard. You lose a lot of information when you observe. So it's hard to reuse them, actually. It's hard to duplicate a qubit. So there's a lot of challenges. Diego says, could you think of this dimmer in 2D since the coefficients can be complex? Actually, it's 4D because it's a whole sphere, but it's 2 complex coefficients. But we can bring it down to 3D and see it in a sphere. Sashwat says, is it okay to denote as vectors? Absolutely, they are vectors. They are vectors with 2 complex numbers. And I see some solutions very well. So Jaime, Russell, Anish, and Dragomir have answered. Yes, very close. Definitely we have, Anish said I, so that's the square root of -1. So yes, it's actually square root of -1. So if you like complex numbers, basically everything in the square, yeah, because the one on the right is square root of square root of 1 and square root of, there's a 2 square roots of 1, and then there's what's in between is I. So the square root of minus 1. If you like complex numbers, any point in the sphere, to answer Diego's question, what the points inside the block sphere mean, they are a pair of complex numbers whose modulus is add to 1, modulus square add to 1. Okay. If you like complex numbers, then fantastic. You can imagine qubits as pairs of complex numbers. But if you don't worry, because actually the first one can be real. We can apply something called a phase change, that you can multiply the top and bottom by a constant, and this you will get the same qubit. So for example, square root of 0.75 square root of 0.25 is the same if you multiply them both by -1 or both by I or both by -I. So therefore, I can make the first number real and positive, and the second one can be any complex numbers. Okay. But for the rest of this talk, I'm not going to worry about complex numbers. I'm just going to think of real numbers. Okay. I'm going to answer some questions. Is the probability distribution or just a unit for this? You can see the probability distribution once we start measuring things. Okay. And is it related to the Riemann sphere? Yeah, I think it's very similar. Pair should provide 4 ways. A lot more than 4 ways, because you can multiply by any complex number. So a pair kind of defines infinitely many. But anyway, the moral of the story is that you can imagine any point in the sphere as a qubit, and it's a pair of complex numbers whose distances squared add to 1. Okay. So I'm going to think of it as square root of 0.75, square root of 0.25. I write the unit function as a little square, but you can normally people think of it as a linear combination of 0 and 1. So square root of 0.75 times 0 plus square root of 0.25 times 1. That's what the wave function is. But I'm going to use the one in the left more often. And I'm going to, as a matter of fact, we're going to have a lot of different representations of a qubit. So in the block sphere, we have a point. Sometimes we'll see it as an arrow. Sometimes we'll see them as vectors. And sometimes it's a wave function. Okay. So this one, for example, the half-half can be seen like that. Then there's this one over here and the total south pole. Okay, so let me know if there's questions about that. There are some special qubits, which are these 4 points on here, which is the North Pole, the South Pole, and the 2 half-halves that are special are root 5, and root 5 minus root 5. And those are called plus and minus. Okay, so basically, in short, classical means you have an on-off switch, and quantum means you have an entire sphere worth of states. Okay, so something weird is happening here, because how much information can I store on a bit? Only a Boolean, right? Only a 1 or a 0. How much information can I store on a qubit? Right? Well, it's a pair of complex numbers. So in particular, I can have any real number. I can store the entire, infinitely many integers, because that's my decimal representation of my real number. So all of a sudden, I could easily store the entire Wikipedia in a qubit, right? All the information there is, because I have infinitely many digits. So what's the catch, right? There's got to be a catch, because I'm not, and Diego got the catch. He says you need to measure. Exactly. The catch is measurement. Okay. Because whenever I store a lot of information in my qubit, but the moment I look at it, I lose all of it or big chunk of it. So we have to be smart to try not to lose, to try to capture as much information as we can. So the measurement works as follows. Let's say that I have my quantum state, which is in a superposition of 0 and 1. The moment I look at it, the thing makes up its mind and says, I'm going to go full up or full down. and you're never going to know what state it was previously. Okay. In other words, when we apply this observation, and I'm going to denote this observation as this little sign that is like a meter, then you, with 50% probability, go up or 50% probability go down for this particular qubit. The probabilities are defined by the amount of up and the amount of down that I have on my qubit, right? So for example, this one is a square root of 0.97 up and square root of 0.03 down. Well, that one's going to go up with a probability of 97% and down with a probability of 3%. So most likely I'll get up, but I will never know what the probabilities were beforehand. Okay. So quantum computing is about playing with those qubits before you observe them, so that when you observe them, you get the answer the question that you wanted to ask. Okay. So some more examples. If I have this one, it goes up with 50% up or 50% down, and this one goes up with 97% or 3% down. So I kind of imagine it as like as if just there were two possible universes, two possible scenarios, and in one of them the qubit went up, and in one of them the qubit went down based on the probabilities. So another way to imagine is if we're at a magnets, right? You put it with two magnets, and the qubit kind of decides which one it joins based on, and the higher it is, the more likely it'll join the up magnet. This is how it's going to look in quantum circuits, and we're going to see quantum circuits in a few minutes. Basically, we have a qubit, and the qubit goes through the circuit and gets changed and then goes out of the circuit. So not very different from like electronic circuits where current just passes by. Here we have a qubit passing by, getting transformed, and then passes by again. Any questions? So if I were to have the qubit 10 times, what this says is that if I measure it the 10 times, like if the sprites are 0.7 and 0.3, then roughly 7 times out of 10 is going to go up, and 3 it's going to go down. So let me tell you a bit more about quantum gates. Let me stop and see if there's any questions.
Looks like there are a couple of questions in the chat window.
Uh-huh.
Yeah. I'm kind of wondering, should we just kind of, bucket all the questions till the end, just so that we can, because some of them are not connected. So
yeah, I'll see if there's anything that I can answer at the time, and if not, I'll keep them to the end. Right?
Absolutely, yeah.
And a few of them I'll see that I can answer them in a minute. So
and I can also collect all the questions and email it to you later. So if you want to take
okay,
back
sure.
answers, that'd be
yeah.
good too. Yeah.
Okay, sounds good. So classical gates. So in the same way that computers have transistors and classical gates, for example, the and or not XOR, quantum computers also have gates. So what's the not gate, for example? Not gate turns a yes into a no and a no back into a yes. Well, quantum gates work very similar. There's a not gate that turns your up qubit into a down qubit. There's actually several of those. And this one back to up. And you can pretty much imagine every rotation of the sphere as a different gate. So there's many gates. In particular, there's 3 rotations. One rotation is in the x-axis by any angle. So that we call it Rx. So it's just basically takes your sphere and rotate it some number of degrees in the x-axis. Then there's the y-axis, which is called Ry. And the z-axis or the z-axis, depending on where you live. And that one rotates the sphere like this. Okay. So lots of gates. And we can think of them as matrices, because if we thought of qubits as vectors, then a rotation is just a matrix that transforms my vector, that I can multiply by the vector. So here are the corresponding matrices. If you like to think matrices, think this. If you don't like to think matrices, imagine a sphere rotating. That's all you need to know. In particular, for some angles, you have the one that turns 0, 1 into 1, 0, right? This is for pi over 2. So you have your not gate as some of several different ones of these gates. And that's the not gate, the one over here. There's also another one, the Hadamard gate, which is a different type of rotation. And this one just oscillates between the 4 popular states. It takes your 0, turns it into a plus, your plus turns it into a minus, your plus into a 1, your 1 into a minus, and your minus into a 0. So this one's particularly special because it takes a pure state, which is diff up, and turns it into a superposition of 2 states. So it creates the pure superposition. That's why it's important. And here's the matrix corresponding to that one. So it takes 1, 0 into root half, root half. Okay. So if you, there's the link for the labs, and don't worry about them now, but you can actually simulate a coin toss, right? With this, you can simulate a coin toss because you can take your qubit, you can apply an H rotation, and then measure it, and that goes 50-50, 50 up, 50 down. So the first lab actually shows you how to simulate just a coin flip. So let's look at something very strange, that is entanglement. And so entanglement, basically, the way I like to think of it is that the really weird part of quantum computing is not so much the qubits, but the relations between the qubits, the connections between them. In the same way as for humans, you don't just study humans separately, you study their relations and their family society. In the same way, qubits get really interesting and powerful when you look at entanglement. So entanglement is a very weird concept, but I like to imagine it as like, let's say you and I break a wishbone, right? Let's say Sri and I break a wishbone, and then we don't look at what each one got, but we take it away, and I go far away in another galaxy, very, very far away, and I look at mine, and let's say I got the long piece, so I know that she got the short one, right? So all that information traveled really fast because I know all of a sudden, right? So that's a bit of a representation of entanglement, even though it's much stranger than that. I like to think of it also as this. Let's say that we have 2 people, and they're happy or sad with a 50% probability, right? And so they're both happy with 25% probability, both sad with 25% probability, et cetera, if they don't know each other, right? Because they're completely independent. The happiness of one doesn't affect the happiness of the other one. So therefore, the 4 scenarios, happy, 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 sad, sad, happy, sad, sad, appear with equal probability, right? Now, what happens if they're entangled? Let's say that they're happily married or something. So when one is happy, then the other one is happy immediately. And when one is sad, then the other one is sad immediately. So I have to only ask one of them. So if I ask one of them and she says happy, then I know the other one is happy instantly. So therefore, in the 4 scenarios in the right, only 2 of them happen because the happy, sad, sad, happy don't happen. And all of a sudden, the other 2 turn into 50%. So that means these 2 are entangled. Okay. And that's the math that happens when 2 qubits are entangled. If I have 2 qubits that are both in half-half state, then my 4 possibilities are each 25% to find them in up, down, up, etc. if I measure them separately. But if they're entangled, that means if I look at one, then if I measure one, then I know that the other one is also, and it's up, then they know the other one is also up. So therefore, the probabilities are different. They're not 25, 25, 25, 25. They are 50, 0, 0, 50, right? And that's actually the Bell state. So that's the simplest of the simplest of all the entangled states, so the pure entangled state. So let's do a quick quiz. Okay, the quiz is the following, just to see. If I have independent people that have never met before and they don't affect each other, and one is happy 70% of the time and sad 30%, and the other one is happy 60% and sad 40%, then what are the probabilities for both happy? Help me out. And while I give you a minute to answer that question, I will look at some questions. So tell me what's the probability of both being happy on the chat, please. I see a question. Probability stats help with quantum computing? Yeah, definitely probability. Quantum computing is all about probability. 42 is the answer to everything. Yes, exactly. The product of the two numbers, right? So 42 is the probability that they're both happy. Then in the same way, 7 times 4, 28 is the probability that one is happy, one is sad. Then 18, thank you very much to all who answered. And 12 are the 4 probabilities. So if this happens, they're not entangled. But if anything else happens, then they are, sorry, if this happens, they're not entangled. But if anything else happens, they're entangled, right? And this is called a tensor product. So a tensor product is when I store when I assume two things are not entangled, and I store the 4 probabilities, okay, the products. Now, if they were to be entangled, for example, if the probabilities are anything else, then definitely these two are entangled because the probability of one measurement depends on the other one in some way, even if it's weak. So the way to tell is if these two numbers equal, is the product of these two numbers is the product of these two numbers, they are not entangled, but if they are different, then they are entangled. There's some technicalities there, but you can think of it for the most part like that. All right. So this is just another way to look at it. If I have that my tensor product is given by the independent products of the two, then I know that they're not entangled. But if my products are different, then they are entangled. And so for two non-entangled qubits, I can write the tensor product like this. But if they are entangled, there's no way I can do that. So that's a way to tell that two things are entangled, and it's when I'm unable to write their equation, their wave equation for both of them as a tensor product of the wave equation of each one of them. And so we'll denote it with this little green arrow. Okay. And now, just like we had gates that manipulate one qubit, we also have entangling gates. So we have gates that can manipulate 2 qubits and either entangle them or disentangle them. This is the equivalent of what in the classical case would be the AND and the OR, right? So the AND and the OR take 2 qubits and turn it into 1 by saying, you know, if both are 1, then my result is 1, or etc. In quantum land, this does not happen, right? But so the AND operator is this one, and the OR operator is this one. But as I said, in quantum land, you cannot do that, because in classical land, I can take 2 qubits and send it into 1. In quantum land, everything needs to be reversible. I need to have, I can have time in the opposite direction, and it should work. And so you cannot lose information. Now, an AND gate loses information, because if I have if the AND gate gives me if the OR gate, for example, gives me a 1, I don't know what came back. I don't know if it was a 0, 1 or 1, 0 or 1, 1. So I lost information. Quantum, you cannot do that. So the gates all have to have the same number of inputs than outputs. That's the rule. And it has to be reversible. So it has to be unitary matrices, matrices that are invertible, actually. Who can help me here? This is the C0 gate, and the C0 gate does the following. Now, who can tell me what the rule is for the C0 gate in the chat? Give you guys a minute. Control not, yes, that's the control not, correct. If the second qubit is 1, then flip the first qubit. Very similar, yes. If the control is 1, do the XOR operation. Yep. You guys got it. So it's where am I? If the up one is, if the first one is up, do nothing, and if the first one is down, then flip the second one. That's what the control not does. So it looks at the first qubit, And if it's down, then it applies a not operation on the second one. But if not, it keeps it the same. So we can see it as this, right? And Diego was correct. AB becomes AA plus B with a binary plus. Yeah, exactly. So it does the following. It just flips the up down, the down up and the down down. So one can see it as a 4x4 matrix, right? Because now I'm operating on vectors of length 4. A qubit is a vector of length 2. A pair of qubits, a tensor product, is a vector of length 4, right? So I can see it as this matrix, which when applied to this vector, I really just flip the third and the fourth entries, right? And so when we have, let me show you what the Bell states are. The two main entangled pairs of qubits are the Bell states, which is the one that is 50% up, up, and 50% down, down, and the one that is 50% up, down, and 50% down, up. Those are the most common Bell states. And so another exercise that we have in the second notebook is, can you entangle two qubits? So imagine if you have all these circuits and you wanna entangle, you wanna start with only up, up. So you start with 0, 0, and you can create some circuit that entangles them so that returns your half up, up, half down, down. So I encourage you to look at the GitHub repo that will share and give it a try yourself. There's a solution, and there's a quiz and a solution, and this is really what you want. And let me see if I have the. Yes, I believe this would be the actual way to do it. You apply an H and you apply a C naught. Let me show you here. So this is the way you entangle two qubits. I start with my qubit 1 and my qubit 2 both in the up position, and I apply a Hadamard gate. So my qubits are 1, 0, 1, 0. I apply the Hadamard gate. What does the Hadamard gate do to the top one? It completely entangles it. So it sends it from up to half, half, right? So that's what my H does on the top. I still have two unentangled qubits, but then I apply the C naught. So how do I apply the C naught? Well, I have, oh yeah, I see that Rugas actually answered the question using Hadamard gate followed by C naught gate. Good job. So the tensor product of these two is this, right? Root 5, 0, root 5, 0 is still unentangled. But when I pass it through C naught, remember what the C naught does? It flips the third and the fourth. So it does the following. Check it out. It flipped this too. And so now I have an entangled state. So with an H and a C naught, I can create from a non-entangled state to an entangled state. This is super important because this is the meat of everything, right? And so I've entangled my state with a little quantum circuit. Now, there are some coupling gates that do this more directly. So there's the XX, the YY, and the ZZ that also, if you apply it, it entangles them, and it's like the equivalent of a high dimensional rotation in the 3 axis. All right. So I like to think of the Ising coupling gates as like sort of something in between, right? Something that goes from, doing nothing is going from up to up, and completely flipping is going from up to down, down. And the Ising coupling gates send it to a state in between, from up to like half up, half down, down. Okay. Just give a little bit of this. All right, so that's the quantum part. And I think maybe we can take a couple of minutes break, since the rest is going to be the actual machine learning, the quantum machine learning part. So what do you say? We take 5 or?
We can continue. It's already 12:20. So okay. I'm wondering, if we could just continue.
I don't mind
And
continuing.
then, we'll save maybe like the last 5 to 10 minutes for question answers.
Sounds good.
Yeah.
So now I'm going to show you, now that we know what quantum computing is, I will okay, I see a lot of questions that I think either I answer,
Yeah, maybe
either I'm
you
answering
can
next,
maybe
or
take
I'm
like a
gonna
5-minute Q&A break, and then we can continue. Maybe.
Perfect. I'll do it at the end. So now here's the thing. Let's remember that we could entangle, we could create one qubit into a superposition by applying the H, right? Now we can create two qubits, turn it into a superposition of 2 by applying a C naught, and a Hadamard. Now, how hard do you think it is to go from the 0, 0, 0, 0 state to the half 0, 0, 0, 0, half 1, 1, 1, 1? You know what I mean? Basically creates it's called a cat state. Let me ask that question. How hard do you think it is to go from up, 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 all the way to half, up, 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 down, 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 down? So that's 4 qubits, entangling 4 qubits. Can we create a quantum circuit for that? And so the answer is that's actually really hard. If you start putting gates and things like that, it's very hard to figure out the right circuit for entangling more gates. And so the answer is we are going to use machine learning for that. Okay, so let me explain for four qubits. What do we have for 4 qubits? We have 16 possibilities, right? From up, 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 all the way to down, 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 all the possibilities. And I can still have a wave equation for this, so as long as I have numbers whose squares add to 1. And I can express it like this, right? So if I can create a Bell state, it goes from up to superposition, and I can create a superposition state of 2. Then the answer, then the question is, how do we do to create a superposition of 4 qubits? And so that, as I said, is very hard. So we're going to use a slightly machine learning approach. Actually, not a slightly, a machine learning approach to create that state. And we're going to use it with do something called a quantum circuit Born machine. This is a paper that's actually written by, this is my manager here at Zapata. And it's a bit of a neural network, but quantum. So it looks like this. So let me show you. This is the meat of things. Okay, I'm going to have a quantum circuit with a bunch of gates. Now these gates are going to have angles, but I'm not going to know the angles. These angles are just parameters in the same way that you have parameters in a neural network. And then I'm going to try to find the perfect parameters to solve the problem I want. So that's machine learning, but in a quantum computer. Okay, so here are my 4 qubits, all pointing upwards. They get rotated by this X gate by some angle. Then they get rotated by the Z gate by some angle. Then there's this XX gate, which entangles them in some way. There's this other XX gate, which entangles the first and the third in some way. And then this other one that entangles the first and the fourth in some way. And then I observe them, which means everything goes up or down with some probability. And then I get what I wanted, which is up, down, down, up. So I'm going to say that my circuit took up, 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 and turned it into up, down, down, up. That's one iteration of my circuit, right? Now I wanted something else. So I'm going to adjust those angles so that I get what I want. And that's a QCBM. That's it, right? So if my circuit were to give me this superposition from up, 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 all the way to like a humongous superposition of 4 states, then that I can draw it as bars that add to 1. And all I have to do is find the one that gives me the correct bars. Now there's a small problem, and it's that as I said, you cannot, when you measure it, you lose all the information. So I'm never going to know if all these numbers, 0.01, 0.10, 0.09, I'm never going to know them. All I'm going to do is get one observation, but that doesn't matter. I can still do it. I just have to run it many times. So I run my circuit once, and I get, let's say, down, up, down, up. So I record my down, up, down, up. Then I run it again. And let's say I get up, down, down, up, down, up, up. So I record that one. If I do this many times, eventually I get a faithful probability distribution that tells me what was my wave equation. I'm never going to know the wave equation, but if I run it many times, I'm going to get something very close to the probabilities that I wanted, right? Feel free to stop me if this doesn't make sense. And so if I, for example, if I had my perfect circuit that creates the superposition of 4 ups and 4 downs, then ideally, after I sample this many times, it would feel like I get 0, 0, 0, 0 one half of the time, and 1, 1, 1, 1 one half of the time, and everything else 0 times. Correct? So that's what we're doing. And so the training process is very much like machine learning. I have my circuit, I have my input, which is 4 ups. I run it many times until I get an idea of with how much probability I get each one of my 16-bit strings. And then I check what I'm supposed to get. I wanted to get the full superposition. So they're not very similar. My obtained and my target are not very similar. Well, I can compare them. How can I compare them? There's ways to compare distributions. Okay. And then I do just like I do in machine learning. I would try to use this distribution, this comparison, to update my angles just a little bit so that I get something slightly better. And that's pretty much it. That's the machine learning concepts applied to quantum computing. So first, I'm going to tell you how to compare, and then I'm going to tell you how to update the angles. Okay. And yes, I think Oscar says this is where you mentioned that it's hard to duplicate. Yeah, absolutely. It's hard to duplicate, but I can run it many times. What says using backpropagation, it's pretty much backpropagation, right? Except finding derivatives is hard because I can't go inside the quantum circuit and take derivatives of the angles, right? But I can do other things. So here, let me give you an idea. Basically, the training process called DDQCL, Data-Driven Quantum Circuit Learning, I believe, is makes me go from whatever initial angles I had to the perfect ones that I have. Okay. And Farid asked, are we doing the training process by quantum computer? Actually, most of the training process is done by a classical computer. I'll show you how. So to show you the example that we're going to do in the lab that I have, that I may be able to run it, we have the bars and stripes data set. Has anybody seen the bars and stripes data set? The bars and stripes data set is basically in a rectangle of m and n, m length n, m and height, width m and height n. All the images that have either a bunch of bars or a bunch of stripes. So here are all of them for 3 and 3. You can see that if all colored and all non-colored is also bars and stripes. So what we're going to do is encode it as a quantum state. So this, for example, I'm going to encode it as 001, 001, 001. So 9 qubits to encode this particular state. I'm just going to reading the rows from top to bottom. Up, up, down, up, up, down, up, 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 down. And so if I have, for example, all the 16 states, all the 16 colorings of a square, then I have my 16-bit strings, right? And so what I'm going to do is I'm going to try to build, I'm switching the problem. Before I was trying to build the 0000 and the 1111 half at a time. Now I'm trying to build the bars and stripes, each one 1/6 of the time. Okay, so I want everything to be 0 except for my 6 bars and stripes, and each one appear with square root of 1/6. Is that clear? So my bars and stripes distribution is basically this one, right? Here I have my 16-bit strings and 1/6 on all the ones that I want and 0 on all the other ones. So it looks like this. This is my wave equation. Okay, I would write as square root of 1/6 times 0, 0, 0, 0 plus square root of 1/6 times 0, 0, 1, 1, etc. And so my QCBM is going to go from here to here. Okay? We're going to train it, my circuits and the right angles to go from here to here. So there's a few things I haven't told you. One thing that I told you is how do you compare the two distributions, right? Because I told you that we get a distribution and then we compare it to the one we wanted. How do we compare it? Well, there's different ways to do it. You can use KL divergence, log likelihood, MMD. You can use there's one where you move sand from one distribution to another one, etc. Let me show you KL divergence. KL divergence is simply a formula that tells me if two distributions are similar. And so, for example, for these two, I get a small number. And for these two, I get a large number. And the formula is summation of p of x, logarithm of p of x over q of x, or an integral if they're continuous. But the idea is that if the distributions were the same, then p of x is equal to q of x. So my logarithms are always logarithm of 1. So that's 0. And the more different they are, the higher the KL divergence is. Okay? So that's it for comparing distributions. And the next one is minimizing a function. So I told you how to compare one, but now I haven't told you how to update angles, right? Like how is that backpropagation process? So in neural networks, it's easy because you just take a derivative and use the chain rule. But in quantum land, you can't even look at things. So how do you take derivatives? One way to take derivatives is to take a sample and then a sample with a slightly bigger angle and a sample with a slightly smaller angle and subtract them, and that gives you a bit of a slope. That's hard, but it's doable. However, we have several methods that do not need a derivative, so they're non-gradient based. I'm going to show you one, which is CMAES. I'm going to show you two, CMAES and particle storm optimization. And the idea is they're not gradient based. So with gradients, you take a derivative, and that tells you how to make a function smaller. In the non-gradient base, you don't take derivatives, but what you do is you have several points helping you search the space, and then you use their information to search the space in a smarter way and be able to find a minimum. So imagine that we're going to minimize this function, and the minimum is here. What we do is we hire a bunch of friends, and we tell them, you talk to each other and figure out how to find this. So let me show you CMAES, which is called Covariance Matrix Adaptation Evolution Strategy. It's an evolutionary algorithm, and it's beautiful. I really like this algorithm. Let's say that this is my function, and the scale is on the right. So yellow and white is big, and then red is medium, and then black is dark brown is slow. And I want to find the ideal point, which is this point over here, right? The lowest point seen from the top. So what I'm going to do is I'm going to plot a bunch of random points. And I'm going to say 5, but think of any number. 5 points. And now I'm going to use normal distribution. So a normal distribution is like a bump in the road, right? It's just like a bump in a blanket, like. And I'm going to see it from the top, which is like this. So this is that bouncing from the top, right? The darkest green is the top, and then it just goes like this. So if I have a bunch of points, I can find the normal distribution of those points by finding the mean and the variance. And so what I'm going to do is evolution, right? I have a population of 5 points. Then the best of them survive. And then out of those, I'm going to reproduce them and have more of them. And then the best of them survive, and then they reproduce and have more, and then the best of them survive, and so on, as follows. I'm going to, first of all, which are the best 3 of these 5 points? Well, the ones that have lowest value in the function, so the ones that are in a darker place. So this yellow one on the left and on the bottom, they go, because only the best survive. So these 2 die. And now I have a stronger population of just the 3 strongest points. And then I'm going to find the Gaussian distribution that fits those 3 points. So it's, let's say, this one. Okay, this is where they came from, imagining. And now these points die, right? But I'm going to sample 5 new ones from that particular Gaussian. So I'm assuming that these 5 are a little better than the previous generation because they are the kids of the best. And again, I'm going to let the top 3 survive. And I'm going to fit a new Gaussian distribution to them. And then they die, and 5 new are born from that distribution. And then the 3 top remain. And then I create a new distribution. And then I sample 5 more points. And then I pick the top 3. And I create a new distribution. And you can see how this process is doing well, minimizing the function, right? Because I'm always getting a slightly better set of points until one day, boom, I'm getting at a pretty good place. I'm at a place where the function is at a good place. Question from Ajwar and Emily. Can we use simulated annealing? The answer is yes. You can also do simulated annealing for this. Emily says, is the CMAS method more or less likely than gradient methods to get stuck in a local minima? It's just as likely, and you have to do just the same kind of things, heuristics to get out of it. CMAS is particularly good because it tries to explore the whole space, right? Not just a little part of it. Gradient descent tends to explore only a tiny part of the space. CMAS kind of looks at all of it. So I'd say it's maybe less likely, but it still can fall into all kinds of problems. Let me quickly show you another one called particle swarm optimization. So particle swarm optimization works as follows. You have 5 friends that talk to each other. Okay, so at every point, they're moving around all over the place. And at any point, they have 3 numbers in mind. They have their current velocity. Okay. Then they also record their personal best. So what is the best point that what is the lowest point that this person has already visited? They keep track of that. And they also keep track of the group best. So like, what is the lowest point that somebody from the group has visited? And with those 3 pieces of information, you add the 3 vectors, and then that point is going to take a step in that direction. And they all do the same thing at the same time. So they do it, and then they do it again, and then they do it again, and do it again, and do it again. And you can imagine that this, if you're finding better and better team bests and personal bests, this will minimize the function, hopefully, right? There's a hopefully attached to every one of these algorithms because there's some probability. But that's the idea. Okay. And so I think with that, we're pretty much done with the theory, right? This is the training process of the QCBM. Let me put it into more formal terms. You start with a random parameterized circuit, okay, with some random angles, and then you from that you sample it enough times until you get a distribution. Your distribution, you compare it with the one that you want to obtain using some cost function. Here's the scalar versions or negative log likelihood. And then you use an optimizer, which could be gradient or not gradient based, to update the angles in a way that that decreases this function a little bit, and then you loop for a long time, updating your angles until you get the circuit that you wanted. And that's how you create circuits. And so that is like building circuits, but it's also machine learning, and that's how you generate things with machine learning. And notice that generation comes up pretty easy of machine learning because all you have to do is measurement, right? Generation in classical machine learning is sometimes hard because you have to pick a pseudo random number and then send it through the network, and or maybe things like RBMs. It's hard to sample. In quantum computing, it's very easy to sample. All you do is run your circuit and observe. That's why generation comes out natural, right? And if you want the winning angles, these are the winning angles for the Bars and Stride distribution. And also you can use more complex architectures, right? This one does much better. So this is just like in neural networks, you have complex architectures. And so here's the one that wins for this one that pretty much builds RBMs. So in this one,
so Louis, do you want to briefly talk about like how do you set up the labs? I can share the labs.
Sure. Yeah.
Later.
We have a repo. We have a repo, and there's installations, right? So you need Python, NumPy, PyQuil, Quilk, and Rigetti. So you need to install a few things. I'll let you go over these instructions. And then you need to, in a terminal, you need to run Qcbm-s and Quilk-s. And so while you take a look, and if you want to ask any questions.
Are there specific computational needs, or you could run it locally?
Locally. I run this locally.
No GPUs required?
Nope.
Okay.
No GPUs. This is a simulator. This is not a quantum computer.
Right.
I'm running a simulator. Yeah. So here is my function that creates the bars and stripes data set. Then here, whoops. These are my 3 topologies. So these are the, you know how I mentioned that there's this architecture and this other architecture, and there's 3 different architectures. So there's the all connected one, which is this one. There is the star, which is this one. And then there's the line topology, which is join first and second, then second and third, and then third and fourth. Yes, I can share the GitHub repo. One sec.
We'll also be sending out an email with all the links you sent out.
So I define my architectures. Then these are the initial parameters. This is where I define the quantum circuit. So I'm putting the angles, the NOT gates, the Y gates, etc. This is my cost function. This is my KL divergence. This is where I call the particle swarm optimization. This is the optimizer that was searching in the space. And here is finally my training process. And hopefully it won't make me look bad. You can see on the right, the red distribution is what we want, and the purple distribution is what we have. And on the left, you're recording the error. So notice that as the KL divergence gets lower and lower and lower and lower, the purple bars get closer and closer and closer to what we want. You see it? 20 iterations, 25 iterations. Come on. Hey, got stuck. Let's give it a second. And in the meantime, I will answer some questions.
So I actually had a couple of questions.
Go ahead.
Where do you see, like, you know, what kinds of clients do you typically work with at Zapata, and how are people, you know, exploring / using these technologies? What's the state of the art? Like, what kinds of applications are currently being used?
Yeah, no, it's a great question. For generative machine learning, it's an exploring phase right now, but in terms of research, we're trying to find the state of art is always finding quantum supremacy, right? So the moment you can do things like generating data sets that already exist, that would be wonderful. Obviously, there's not, you cannot fit an image into qubits because there's not enough qubits in a quantum computer for that. So, but one thing you can do is do it in the latent space. So for example, the generative adversarial networks, they take your data, they crunch it, and then they bring it back up, right? The discriminator makes it small, the generator takes it back from small to big. In this space, there's wonders you can do because they're small enough, and you can use it to you can use your quantum algorithms to explore that space in ways that may be better, faster and better, independently of speed, than what a classical computer would find, right? Because you're trying to model the right distributions. And so those are advances you can make. You can also use it to generate other type of data, financial data, etc. Or even generate solutions to things, right? Like if you're doing, for example, portfolio optimization, you can find solutions using whatever classical algorithms you have, but you can also maybe generate new solutions using this type of models. And sometimes the solutions you generate are some solutions that you would not find using your regular optimizer, right? So there's many things you can do in generative learning. I'm going to run this thing again because it stopped.
Have you explored anything in like synthetic data generation?
Yeah. We can try to, especially things like financial data, right? Like you have to generate synthetic because there's not enough of it. So you can try to use sort of enhanced GANs for that. You can do a lot of you can do a lot of things there.
And how do you kind of sell the value proposition at this point in time compared to traditional computing, in terms of I'm kind of looking at like pragmatic approaches at this point in time for some of the financial community we work with. Have you seen like use cases wherein they are exploring or even trying things out in the quantum side of things?
Yeah, definitely. And there are some places that are looking for it, that are looking for quantum a lot. Anything with chemistry, because you're modeling particles, modeling molecules is very hard, and quantum computers seem to be better at that. Financial optimization. So also when you have big problems of optimizing, can also be fit into quantum computers. So those are the three main areas where quantum computing is being used, but slowly machine learning is becoming one of the important ones too.
And how about like cryptography? I mean, that's the biggest scare.
Cryptography is huge because the moment the quantum computers are big enough, they're gonna break every code, right? With Shor's algorithm, you can break RSA cryptography very easy by factoring numbers. And so something that took trillions of years to solve for a classical computer can take a few hours for a quantum computer. And so cryptography needs to be reinvented when quantum computers start getting bigger. I think you need to use some kind of entanglement or teleportation or something.
Crystal ball say from
Say that again, please.
So how many years away are we from pragmatic quantum computing?
Yeah, I wouldn't know how to, I can't put a number to it, but I would say that it's definitely a when and not an if. So I think it'll be soon. While I keep answering questions, since this stopped for some reason, let me actually run another one. This is the one we did in orchestra. I'm not gonna go over the orchestra demo because it's a lot, but I'm just gonna show you a pretty picture. This is what we did in orchestra, where we coded the algorithm, and it's searching the space. You can see the dots are the other points, and this is the distribution that we're trying to obtain. So I'm just gonna let it run here. Sorry, say that again about benchmarking.
So in terms of approaches other organizations like IBM and Google are taking, versus the approach your organization is taking. Have you done any benchmarking or looking at?
Our approach is quantum software basically. So IBM and Rigetti and Honeywell, they have quantum computers with hardware. And I see somebody asked more about that. So our product is not a quantum computer. but it's the quantum software to run a quantum computer. So we let people run code on any of those, on any computer that they want, or different ones, and we provide the packages and the software. Yeah, so that's how it's different.
And is the value proposition that you write once, run anywhere?
Yeah, you can write from any software that you have, any package that you have, and any quantum computer that you want to have, that you want to use. You can all put it together in one little package. That's mostly the value proposition. Yeah.
Cool.
Yeah, let's see what questions are there. I'm just gonna answer random ones, and I apologize if I missed one. Please feel free to send it again.
Yeah, and I'm gonna consolidate some of the questions,
yeah,
and send that to you in case.
AJ says a very silly question about how to convert integer or text data into qubits. Oh, not a silly question at all. How to convert integer or text data into qubits. So there are ways. One of them is, if you have ones and zeros, turn them into ones and zeros qubits. Another one is to actually make it the angles of something. So you can start with zeros and encode your data as angles, and then measure that, or like not measure that, but apply those gates, and then you have a qubit that stores your data, right? So there's many ways. It's challenging. It's not as obvious as with general classical machine learning, where you just feeding the data. Avi says, can we get the slides? Unfortunately, not the slides, but the video. AJ says it's similar to backpropagation. I think I mentioned it, that it is similar. How do you gate the state of a qubit before passing it through a gate, says Pierre. You cannot. You cannot get the state of a qubit. I can have a qubit and will never know the state. The moment I observe it, I lose that. However, I can do things to it before observing it, and that's what's special. Where can I learn quantum machine learning, says Ajwat? There are not too many resources. I know. Well, I'm working on a few things. So we'll look at Zapata, YouTube, and stuff. We'll be having tutorials and things like that. For now, check the tutorials here. It's a good way to learn. You mind talking a bit about quantum teleportation, says Laxman. Yeah, let's see. Yeah, quantum teleportation is just similar to, like, when you pass information, you can pass information from one place to another by entangling qubits. So yeah, it'll take me longer, but I can give you some resources. Let's see. Why don't we use inside the sphere, says Ferit. Physically, quantums can only be defined as when the sum is, because you can have the electron in different states, but you can have it in combination of states, but you can never have it in, they always have to add to one. So you will always have points in the sphere. Ugra says, is the cost function evaluation done on the classical part or of the system or on the quantum part? Yeah, great question. Qcbm is a semi-quantum. Nothing is pure quantum, barely ever. There may be things, but quantum algorithms are always a big chunk is classical, and the quantum part is just for some part of the algorithm that's a bottleneck. But for example, here we do the quantum to prepare the state, but when we measure it and we create the distribution, that's classical. KL divergence is classical, and the optimizing part is classical. So most of it is classical, except for the part of running the circuit. Yeah. How are we doing over here? Well, it seems like this, after 600 iterations, this QCBM worked. So let me give you some parting words over here. If you want more of this simulation, there's a YouTube video from a colleague of mine that you can find by scanning this code in your phone. And there's more of the orchestra part of how to run this QCBM on a quantum computer. So I invite you to take a look at that. And some links. Orchestra.io is where you should look for the tutorials, orchestra.io.docs. If you want to see upcoming trainings, we have a lot of trainings. We have demos. You can request access at orchestra.io because you need access to use this. And then this is my final slide. So I have there's a book, Rocking Machine Learning, that I have, and I encourage you to take a look. The link is right here. And the discount code for 40% is Serrano PC. So feel free to use it for 40% code of discount. Like I said, this is my YouTube channel where I have a bunch of videos where I explain things in this sort of friendly way, mostly machine learning and probability, math, etc. This is my Twitter. And I have a page where all this is called Serrano.academy. So you can find the book there, the discount code there, the videos and everything. And when this talk is on YouTube, I'll share it there. That's pretty much all on my side. So I'm happy to discuss or answer questions or anything else. Thank you for your attention.
An absolute pleasure, Louis. What I've done is, I know we are very close to 1 o'clock. So I've also taken a snapshot of all the chat and the Q&A questions. So I'll send it out to you. So maybe if you have some time in the evening, you can just put it. I can just basically take a snapshot of it and then put it on the site so that people can look at the questions. And I've also, this session is being live streamed both on LinkedIn Live and also on YouTube. So it's going to be archived and available to everybody afterwards. And I will also share some of the links you shared with me. And this was an absolute pleasure. I learned a lot. I mean, it's always intrigued me on the innovations which are happening in this space. But I'm kind of grounded to reality in the context of what are the immediate burning problems which are pragmatic and some things. But this is fascinating. I mean, it's one of those things wherein it's not only being able to see it in action, but also to understand the concepts. And thank you for taking time and putting together this amazing tutorial. I really appreciate it. And looking forward to future collaborations. We're running this winter school, and if there are other innovations we'd like to bring in to the audience, we'd love to have that. And with that, I think it's 1 o'clock. It's time to wrap up so that we can get back to regular work, I guess. People are taking their lunch breaks off, and we'll keep in touch. And again, next Wednesday at noon, we're going to talk about some of the innovations, including some of the innovations for such day, about the 10 innovations you'd be interested in for 2021. And we also have many other sessions on interpretable AI and also on some of the key themes in terms of machine learning innovations, which are going to be presented more or less every week throughout the semester. So please stay tuned and do keep in touch. If there's any feedback or any other questions for us, please feel free to let us know. Again, you can reach us as www.quantuniversity.com, and we will be connected and we'll see you online. Thank you so much.
Thank you so much for the invitation. Thank you so much for all your attention, everybody. See you next time.
See you. Bye-bye.